Welcome to lesson number 7. We're going to look at transformations of trig functions, and this is part 1. At the beginning of this course, we're looking at different transformations of functions. Now we're looking at transformations of trig functions. So throwing in our primary trig ratios. So today we're going to be looking at sine and cosine and examining what's going to happen when we change the parameters of a and b as they relate to y equals a times sine times b of x minus c plus d, and y equals a cosine b of x minus c plus d. Remember, we're only focusing on two parameters, and the impact or the effect that these parameters have on a and b are going to be the same for the sine and the cosine function. So the first thing we want to do is think about if I were to relate the change in y or x to these functions, how is that going to shift my graph? Well, remember, if I had y is equal to 2 sine x, if I were to bring this 2 back to the y, then I would have to divide both sides by 2 or multiply both sides by 1/2, which I would be multiplying my y by 1/2. So y times 1, I don't know why I wrote like that, but it's 1/2 y, that's better. In the beginning of the course, we talked about what impact this would have on a function. It was a vertical stretch. So we had a vertical stretch by a factor of 2. So I would have to divide by 2 on both sides, or multiply by 1/2, but it's going to be a vertical stretch by a factor of 2, so a vertical stretch up and down. If I have y equals sine 2x, remember this 2 is acting on my x value, so that would be x to 2x. This would be a horizontal stretch by a factor of 1/2. If I had something like this, y equals negative 3 sine x, there's two things that's happening here. So first of all, if I bring the 3 to the other side, my y is going to be mapped to 1/3 y, but y is also reflected in the x-axis, right? So we have a, not horizontal, sorry, we have a vertical stretch by a factor. If my y is mapped to 1/3 y, then it's by a factor of 3. And we also have a reflection in the x-axis. A reflection in the x-axis. Lastly, I have y equals sine negative 3x, and this is another example where my x values are being mapped to 3x, and I also have transformation, but this time in the y-axis, so x is go to negative x. So I have a horizontal stretch by a factor of 1/3 and that's about the y-axis. And I also have a reflection, and a reflection in the y-axis. All right, so let's look at this next example. It's related to the above examples as well. But in which of the above examples here is there a change in amplitude? So a change in amplitude compared to the graph of y equals sine of x. So where did my amplitude change? Well, if we think about what the amplitude was in the earlier lessons, remember when I was graphing sine x or cosine x in lesson number 6, my amplitude was the amount that, the difference between the distances between my maximum and minimum values of my functions. So first of all, if I were to look at these graphs, so two sine x and graph. And I'll have to change my window settings here. So let's go y max of 4 and -4. Alright, so if I'm looking at my amplitude here, I want to compare these different graphs to see where I had a change in the amplitude compared to y sine x. So that was my graph there, and I have sine x, graph that. So my first one, I have a change in the amplitude, right? So my amplitude is the difference between the minimum and the maximum and the minimum value. So here's my min and max compared to my min and max here. So I know that that is going to be a difference. So graph number 1, and let's compare. Let's think about y. This is a graph that looks very similar to graph 1. So let's see what happens if I were to graph that. So -3 sine x graph. So we had an increase in my amplitude in this next graph. And so graph number 3 also had a change in amplitude. Now let's look at let's look at these other graphs. So there's graph sine x, and I'm going to put this in number 3, so graphs after, but let's go sine 2 of x, and then we'll graph. So this is the first one. This is graph sine of x, the function sine of x, and if we look at the next function, sine 2 of x, there's no change. The amplitude is actually equal, right? It's equal distance. So that did not change the amplitude. But if we look at which ones changed the periods compared to the graph of y sine x, well, we know that the graph 1 and 3 actually had the same period. And so let's look at those ones again. I have 2 sine x, and I'll just look at this one just because it's very similar. So this is the first, this is 2 sine x, and then the next one is going to be my original function sine of x. But look how the period is the same at each point. They have the same x-intercept there. But if we graph -3 of x, so I'm going to clear that, or let's graph sine 2 of x, sine 2x, and sine -3x. So here's my original function, and my other functions are coming in. And now we're seeing that they're actually crossing at different points of my x-axis. So here's the third one. And so 2 and 4, graphs 2 and 4 have a change in period to the graph of y sine of x. Now what we need to do is complete the table here. So the amplitude, and it says to use the graphing calculator. So sine x, first of all. Graph sine x. So the period here, if I look at my window settings, is 2 pi, and that's 360 degrees. That's my x min and my x max, 4 pi. But if I look at the period here, for most of these it's 360 degrees. The amplitude is just 1. If I were to find my minimum value, my maximum value, y equals 1. My minimum value is -1. So 1 plus -1 would be 2 divided by 2 would be 1. So I have an amplitude of 1. If I look at my graph 2 sine x, we've doubled my amplitude, so this would have an amplitude of 2. So I'd have an amplitude of 2, and it's following the same period, so that's 360 degrees. And so let me delete that one. But let's look at this next one, sine 2 of x. So sine 2 of x, and let's graph that. So here's my original function, followed by my other function, which is, and let's look at that one again. So there's my graph. So sine 2 of x. Let's see what's happening here. So I'm actually crossing at halfway, so my period is actually halfway between the period of my original graph. So that means that we're actually at a period of 180 degrees, but I have the same amplitude. It's the same maximum and minimum points of 1. Let's look at this next example, negative 3 sine of x. We'll graph this one now. So this is my original graph that's being placed on here in my next graph, negative 3 sine of x. Well, if I look at this, this is actually tripled my amplitude. So my amplitude is now 3, but it has the same period. So I have an amplitude of 3, same period, so 360 degrees, same period as my original. Sine negative 3 of x. So here's my original function, and my next function is going to follow soon. So my period is the same, right? Or not my period, sorry, my amplitude is the same as my original function, so as sine of x. But if I look at the period has changed. So I have an amplitude of 1, but now my period on this graph is different. And so if we were to look at that change in period, and we're going to look at how to actually get it a little bit later on, but this change in period is actually going to be 120 degrees. We'll talk about how we find these change in periods in a second here. With 5 and 4, if you're starting to kind of get a feel of how the amplitude changes, the amplitude is related to my A value that we're looking at up here or here, and my period is related to my B value. And so 5, because I have 5 there, 1/3 because I have 1/3 here, and here it would be A because of the A here. So describe the effect of the parameter A on the graphs of y equals A sine of x. Well, the parameter A affects the amplitude. So parameter A affects the amplitude. Parameter A affects the amplitude of the function. And in fact, amplitude is equal to A. Describe the effect of the parameter B on the graphs of y equals sine x. Well, parameter B, when we changed the B parameter here and here, we changed the period, right? So the original was 360 degrees, but changing parameter B to 2 and negative 3 here changed my period. And so parameter B affects the period. And it actually affects the period by this formula, which is equal to 360 degrees over B. And so when I changed my B value to 2, 360 degrees divided by 2 was 180 degrees. 360 degrees divided by 3, 120 degrees. 360 degrees divided by 4, this would be 90 degrees. 360 degrees times 2 or divided by 1/2 this would be 720 degrees. And then if b is b, then that would be 360 degrees divided by b. Jet, do you like your ice cream? Next, we'll look at a few short examples. So moving on to class example number 2, 3, and 4. But in all these examples, we're going to be graphing freehand, but also coming up with the equations of our trig functions. And so for y equals a sine b of x, or y equals a cosine b of x, and y equals a tan b of x, these are some rule of thumbs and some formulas to keep in mind. In order to find the amplitude of a function, it's the maximum point, subtract the minimum point, divided by 2. And that goes for a sine function or a cosine function. For a period, to determine the period, in degrees would be 360 degrees divided by my b value. For the period in radians, 2 pi, which is equal to 360 degrees, divided by my b value. When working with tan functions, the amplitude is not applicable because we have infinite values there, right? We're running along our asymptotes. For the periods, for degree and the radian, the measure that we use is 180 degrees and pi, right? These are equal measures. So when we're sketching the graphs, what we want to do is sketch the primary trig ratios, sine or cosine. So if you're doing it manually, sketch those first and think about how those graphs are adjusting in relation to their max and min points. And we're going to look at class example number 2 in order to see how to actually do this. So consider the graph of y equals 4 cosine 2x, where x has to be greater than or equal to 0, but less than or equal to 2 pi. So in this example, we're working with radians. I know what my a value is, and I know what my b value is. So my parameter a is equal to 4, and parameter b is equal to 2. I know that a is equal to my amplitude, so equals amplitude, and that is equal to 4 units. My period, however, is equal to, well, if we refer back to this, period is equal to 2 pi over b, absolute value of b, but period is equal to 2 pi over my b value, which would be 2 pi over 2, which would leave me with pi radians. So my period is equal to pi radians. Now, when I'm placing this on the graph, one thing I could do is start with my point at 4. And I know this is going to go pi radians, and so I know that for one period, so from starting point to what we could call an end point would be pi radians, right? So from here to here. Now, if I go from here to here, I'm also going down. I have a amplitude of 4. So the difference between my max and min point is 4 units, which means that when I go down, it's going to go all the way down to -4. So around here, and halfway the full period would be pi over 2, which would be half of pi right there. And so my graph is going to look something like this, and I'm going to go up, and this is not looking too good right now. I need to curve a bit more. And so halfway between pi and 2 pi, it's going to go back down, and then it's going to reach the maximum point at 2 pi. So and my graph will look something like that. And we can verify this using a graphing calculator. So working with the cosine here, but 4 cosine 2 of x, let's graph this guy. And there we go, looks something like that. And of course, we're only looking for my x values between 0 and 2 pi. And so 0 and 2 pi would be right here, this section of my graph. And we could change that in my window settings, changing the x values. All right, class example number 3, write the equation of a sine function having an amplitude of 2/3 and a period of pi over 6. So the first thing we need to do is we actually need to determine parameter p. So parameter p, or it's not p, parameter b needs to be found. All right, so we got to find parameter p. We're given the period and we have the amplitude. So A, amplitude, is equal to 2/3. But remember, period, we're working with pi here, is equal to 2 pi over b. We have the period, but we don't have my b value. So if I rearrange this, b is equal to 2 pi divided by my period. And the period, remember, is pi over 6. So b would equal 2 pi over pi over 6. So we're dividing a fraction, right? Which means that this would be, so b would equal 2 pi over 1 times 6 over pi. These pi's can cancel out, and we're left with b is equal to 12. If I plug in, so now I have everything I need to form my equation, a sine function with an amplitude of 2/3 and parameter b of 12. And this would be my equation I'm looking for. A cosine function having an amplitude of 3, so a is equal to 3, and a period is equal to 720 degrees. So again, we got to find for b. If I rearrange my equation similar to what I have here, but instead of 2 pi, I'm using 360 degrees, that becomes 360 over my period, which is 720 degrees. So my b value is equal to 1/2. If I plug this into my formula, y is equal to a, which is 3, cosine 1/2 x. That's my final answer. And last one, a tan function having a period of pi over 2. All right, well, amplitude is not applicable, so my period is equal to pi over 2. If I rearrange that formula, b is equal to 2 pi over the period, which is equal to 2 pi over pi over 2, which is equal to 2 pi over 1 times 2 over pi. And again, hold on, what's pi over 2? Yeah, again, we cancel out, and we're left with, oh, sorry, hold on a second. We're working with the tan function. So my period, or my parameter b, is just pi over the period, not 2 pi over the period. So my final answer is 2. It would be pi divided by pi over 2. So pi times 2 over pi then, if I flip this. And my period is just equal, sorry, my parameter b is just equal to 2. That's confusing for you, I know. I'll clear that up in class. But my final equation would be y is equal to my b value, tan 2 of x. All right, this next example, say the amplitude and period of the graph. So we're looking for the amplitude, and we're looking for the period here. So my amplitude, well, what's the difference? I'm starting at 0 here, and this is 3. So that's 3 units. And my amplitude, where do I start and where do I finish? Well, I'm starting here. So 1, and I go to, if I go halfway, that's pi over 2, or 1/2 pi, which means in order to repeat this rotation, I'm going pi radians. Determine the equation of the sine function which the graph represents. I know that a is equal to 3. My period is pi. So I know that a is equal to 3. B is equal to, this is a sine function, 2 pi over pi is equal to 2. My function is y is equal to 3 sine 2x. That's my final answer there. Last example is class example number 5. So the graph represents the effects of tides on mean sea level over a 24-hour period. The graph has equations h of t is equal to a cosine b times t, where t is in hours and h is in heights in meters relative to mean sea level. Determine the equation of the graph. All right, well, let's start with determining what our amplitude and period is. R is R. Amplitude and period are, well, my amplitude, I'm starting at, this is 0, 4 to 0, 4 up to 0. Amplitude is 4, and that's 4 meters. My period, okay, if I'm starting here, I go 1 half a rotation, back up a full rotation. That would be 12 units. This is time, sorry, time in hours, so that's 12 hours. All right, we have A and P. A is equal to 4. Period is equal to 12, which means that B is equal to 2 pi over my period, which is equal to 2 pi over 12. 1 and 6, which is pi over 6. So this function h of t is equal to a, which was 4, cosine b, which is pi over 6 t. And this is my final answer here.